Unido. From Dr. Adrian Ionescu from the University of Cambridge, from the United Kingdom. Adrian Ionescu is going to give us a very interesting talk in different topics that he has been working during the last years in bulk materials, nanomaterials, thin films, and many materials that he has been investigating. Adrian Ionescu is affiliated with the University of Cambridge from more than 20 years, I think, more than 20 years, and in the TFM group of the Cavendish Laboratorio, Department of Physics, the University of Cambridge. Well, he's a very nice friend of us, and also he has visited, también él ha visitado Perú, el doctor Adrian Ionescu ha visitado Perú varias veces, ha visitado varias universidades en Perú y ha dado charlas en la Universidad de San Marcos, en la Conferencia Latinoamericana de Física de Superconductividad y Magnetismo, ¿no? Perfecto. Well, welcome Adrian Ionescu, Dr. Adrian Ionescu from the University of Cambridge, and you can share your screen, please, and start your talk.
Okay, thank you very much, Luis. Thank you very much, ladies and gentlemen, for the invitation. I will try to share now my screen. Let me know if it works. You should hopefully see now.
Yes,
the slides.
Yeah, you can see. Yes.
Yes. Okay. Thank you. So rather than to force you onto a talk on some subjects which you might or might not like, I decided that I would give you a suggested outlook of certain things, as Louis said, on which I have worked on in the last few years. Starting maybe with the introduction on spintronics, but there was already one very good one 2 weeks ago by Professor Desde from Brazil. So maybe I will keep that very short, and then maybe the audience can choose from the following subjects on which I had worked. So one would have been topological insulators. That is one of the subjects which I could present. Graphene ferromagnet interfaces. That is something which we are aiming to publish shortly. Oxide interfaces, what I mean here is europium oxide, lanthanum, aluminium oxide, and the search for a two-dimensional electron gas. Nanoparticles, in particular core shell, single stoichiometry, but core shell particles such as nickel oxide, I would discuss in this talk. I had presented this also that time in Lima in 2017-18 at the conference in more detail. And then cube on hexagon epitaxy. So over the last few years, several materials have been tried to be grown on sapphire or other hexagonal substrates by molecular beam epitaxy or sputtering, other physical vapor deposition techniques, and the problems which have emerged. We had here this case of iron on gallium nitride. And then the last two topics is spin polarized energy electron loss spectroscopy, a technique which we have developed to study the band structure of materials in collaboration with a group in Japan, at the National Institute of Material Science. And then finally, the superconducting diode effect, which I've started working with the group in the material science department at the university. That would be the last possible topic. So each of them are about 15 minutes at most. And I would say if the esteemed audience, I see there are about 18 people now, could raise maybe their hands about the topics, well, I read them out and we choose 2 or 3 and I will discuss those with you. So Luis, can you keep an eye on the reactions, please?
Yes, I think that people are interested nowadays in some of spintronics, oxide interface, and nanoparticles. Okay.
Yeah, well, I mean, could we have a vote? I'm a Democrat, so maybe if everyone could raise their hands, I will read out the topics, and maybe
Okay.
we count the hands and see how much interest are in the different topics. So my first suggestion would be topological insulators. Is there any interest in this? Can you raise your hands if you do have any interest to listen into that? So I look at where is the chat? Luis, do you see the chat?
Yeah, the chat says the superconducting diode effect Professor Albino is suggesting.
Okay. I was guessing this already.
Maybe nanoparticles.
Okay. And maybe one more topic.
Another topic. This says spectronics. Says
Well, the
Ximena.
spintronics is the portmanteau, is the introduction. It's nothing specific. It's so it's just the introduction to the whole of the talk.
There are some students from Kazakhstan here attending, and they will be very happy as well to be quite basic as well. Okay.
Yeah, I will introduce the concepts initially, but then I thought that on the main materials.
Stuart Holmes is suggesting oxide interfaces and diode
effect. Okay. Okay, so I think that the superconducting diode effect has appeared there a few times, so we'll have a look on this.
People, also students are asking for superconducting. Eliana
okay,
from Colombia.
We're gonna look at the superconducting diode effect. No one with the graphene. That was or spin polarized electron loss spectroscopy. Okay. So what else was mentioned? Oxide interfaces. Okay, that is I see here topological insulators and nanoparticles. Okay, what about then? I start with the general introduction, and people can still choose some of the things, and we see as the votes come in what else I will talk about. Okay, so let me start then on spintronics. So we had 2 weeks ago already Professor Resende from Brazil giving a much more detailed.
Can you maximize, Adrian, sorry, can you maximize your presentation so it means that full screen?
It should, at least on mine, it is full screen.
No. It's not full screen. Maybe you need to unshare and then share again your screen.
Okay. I will do this.
Yeah.
Okay, let me do this. Could well be. This could well be, okay.
Para los que se conectan de Perú, vayan dejando sus preguntas en las redes sociales las redes sociales de donde están siguiendo esta transmisión. En Colombia, público latinoamericano, pueden dejar sus preguntas en las redes sociales. Al final de la charla del doctor Adrian Ionescu de la Universidad de Cambridge, los estudiantes van a transmitir sus preguntas. Okay, thank you.
It's full screen now.
Yes, now it's okay. Bye-bye.
Okay, so it was probably because I had stopped sharing for a while. Okay, so you should have now. So there was 2 weeks ago already a quite good talk by Professor Resende. He went much more into detail. I will just outline the field of spintronics, which is a portmanteau for meaning really spin transport electronics. It was also sometimes known as magnetoelectronics when it first started, which is a technology which has been ongoing for about 20-30 years, maybe even earlier. We see in 1971 the spin hole effect, which has been predicted by Diakonoff and Perel. And what it wants to do is to exploit both the intrinsic spin of the electron and its associated magnetic moment. in addition to the electronic charge, which is already used in solid-state electronic devices. And the spin Hall effect, which was that time predicted, has some similarity to a certain extent to the normal Hall effect. In the typical Hall effect, you pass a current through a certain wire, let's say, or it's depicted on the left, and you apply a magnetic field perpendicular to the current, and then you measure a voltage across this wire. And similarly, you can have this spin Hall effect, where you have here, instead of separation of the charges in the Hall effect, you have separations of the spin. Historically, maybe one could say that indeed it started in the 70s with tunneling experiments. Tunneling experiments between ferromagnets and superconductors, pioneered by Tedorov and Mercevey, and maybe with magnetic tunnel junctions from Julier. This was all in the 1970s, but then really it emerged in the 1980s when spin-dependent electron transport phenomena in solid-state devices were studied, such as maybe the spin-polarized electron injection from a ferromagnetic metal to a normal metal by Johnson and Sillesby in 1985. Clearly, the heydays it reached in 2007 with the award of the Physics Nobel Prize to Albert Fert and Peter Grünberg for the discovery of the giant magnetoresistance, abbreviated GMR, which then was used widely in magnetic hard drives. But there were different fields on which we worked during the years, and one was the so-called spin field effect transistor, which was proposed by Data and Das in the 90s, stimulated a lot of research to combine ferromagnetic metals with semiconductors. As I mentioned, motivation was application to the solid state industry. One of the most used was the hard disk drive, still today to a certain extent in use, where you store information in magnetic little clusters as 0 and 1, and you can read it out with your GMR head. I think nowadays it's even TMR heads. But as we know, by now it has been superseded almost by solid state drives. So they are still used today. Many of us are probably using it as a colder storage, as a backup disk. Another very promising development initially was the magnetic random access memory, where you would use magnetic storage elements instead of electronic ones. This promised, it has been developed, but again remained a bit of a niche technology, promised direct access to your computer. Again, I think the concept had been with the time surpassed, but stimulated a lot of research. Looking forward, really, I think where the future lies in the output of spintronics or magnetoelectronics is really the proposed application of spin qubits into quantum computing. And there are a few suggestions how this can be implemented, be it with ferromagnetic insulators or superconductors, and many other suggestions. So I think that is maybe the most fascinating aspect of the potential outcome of spintronics and implementation for the future. So having given this brief introduction, maybe I can have a look again what people were asking: oxide interfaces and diode effects. Okay, let's start there. I might have to share, I think, again. I need to jump a little bit. Okay, let me take you to the oxide interfaces. Right. So
You stop sharing, Adrian.
yeah, I should now share new, and hopefully you should see it. Can you see
Yes,
now?
yes, go ahead.
Okay, so this was some work which we have started a few years ago, but it took quite a long time. It was postulated that when you use europium oxide, which is a ferromagnetic insulator, and you grow this on lanthanum aluminum oxide, you would create a two-dimensional electron gas, which has, of course, quite far-reaching implication if this should prove true. This was all calculated based on density functional theory. And we thought, okay, let's have a look. The major work was performed by one of our students, Razan Abol-Yadayel. And the technique which we decided to use in order to study whether or not this two-dimensional electron gas emerges were based on particle physics. In this case, it was muon spin relaxation and polarized neutron reflection. In particular, we wanted to use low energy muon spin rotation. It's a bit like electron spin rotation, ESR, but here instead of the electron, we study the rotation of its fatter brother, the muon. In fact, it is actually a positive muon. And you create, this was done in Switzerland at the Paul Scherrer Institute. You create a beam of spin polarized muons, which are accelerated and stopped in your sample. So they're implanted in your sample. And the muon has a certain lifetime of on average 2.2 microseconds and decays then into a positron and two neutrinos. And depending, of course, on the internal magnetic field, the muon, which, as I said, is similar to an electron, has spin a half particle, rotates around the internal magnetic field in your sample, then dies, and due to or decays, and then due to conservation of the total angular momentum, emits the positron in the direction of the field to a certain extent. You have two possibilities. You can do this without any applied field, so in the zero field setup, or in the weak transversal field setup, where you induce a small magnetization in your sample around which the muon should process before it's decaying. And then you basically collect the positrons, and you can study the internal field distribution in your sample, the magnetic field distribution in your sample. So we tried basically to use this technique to study this creation of this proposed two-dimensional electron gas at the interface between lanthanum aluminum oxide and europium oxide. I need maybe to tell you a little bit about europium oxide. It is, I said, a ferromagnetic insulator, has a magnetic moment of about 7 μ per atom, a Curie temperature of 69 Kelvin, a band gap of 1.2 electron volts at room temperature, and below the Curie temperature, it has a spin splitting of 0.6 electron volts between spin up and spin down electrons, making it almost 100% spin polarized below TC. And there were a few groups which used density functional theory to predict that when you create this interface between lanthanum aluminum oxide and EO, you create this two-dimensional electron gas, as is shown on the bottom of this slide. They postulated mechanism which they stated to create this spin polarized 2-deck was either that there is a polar catastrophe. That means in the lanthanum aluminum oxide you have stacks of aluminium O2 and lanthanum oxide, and each of this layer are either positive or negatively charged. So you have like an inbuilt electric field, and this inbuilt electric field in the lanthanum aluminum oxide creates a charge surplus at the EOO interface. And because of the spin polarization of the EOO, you have de facto then some kind of spin polarized electron gas at this interface. There were also discussion of thermal interdiffusion or the creation of oxygen vacancies, which should lead to the same result of this spin polarized two-dimensional electron gas. So we said, okay, let's try and see whether these simulations are right. So we had to create first lanthanum oxide terminated, and in contrast we wanted to have also aluminum dioxide terminated interfaces, which was a bit more tricky. We couldn't achieve this. We got a bit of more of a mixed interface depending on the synthesis methods, but we could create this lanthanum monoxide terminated surfaces, which were stipulated to create this two-dimensional electron gas. And then once we prepared the substrates, we grew europium monoxide thin films by magnetron sputtering of europium and europium 203 at room temperature due to co-deposition, and kept it with gold or sometimes with platinum, in this case with gold. Measured then the structural properties to check basically for the termination, either single lanthanum monoxide terminated or mixed terminated, and that we could infer basically by the step heights in the AFM scan here. We did also do XRD and XRR. So XRD to check that we have really grown europium monoxide almost epitaxially as we could onto lanthanum aluminum oxide, and XRR to infer information about the roughnesses between the two layers. I think that my colleague Dr. Newton had introduced you already in his talk the low temperature scanning polar MOC microscope. So I will not dwell too much. This was maybe a month ago or so when he gave his talk. We used low temperature MOC basically to similar as you image the structural domain by atomic force microscopy. You can image the magnetic domains of your sample by low temperature magnetic optical Kerr effect imaging, and you can see the domains. One thing what you see here as well is that the domains have certain shapes, that they are slightly tetragonal and they oppose each other. That is because the lanthanum aluminum oxide crystal is a monoclinic crystal and often twinned. So you never really get a single terrace, let's say, or a single surface with this monoclinic crystals, and instead you get this mosaic forms. We studied then the magnetic properties by superconducting quantum interference device and checked in which direction the easy magnetic axis is. This was all necessary for our final experiments. And then once we were happy that we had the right structure, we took it to Switzerland for low energy muon spin rotation, which we performed there in as I said, weak transversal field and zero fields. The results are shown on the top. And what you have is a kind of an asymmetry as you do a time scan, and the signal decreases in two exponential ways. One with a quick relaxation, a little lambda, which contains information about the magnetization along, for instance, the applied field, and large lambda there, the fast relaxation which contains information about the field perpendicular to the spin precession of the muon. And we then took this information and studied basically, depending on the energy of implantation, you can implant the muons further away from the interface, so into the bulk of the europium oxide, or closer to the interface, so where we were expecting the two-dimensional electron gas, and we wanted to compare if there is any difference between the information collected in the bulk or at the interface where this this spin polarized 2-deck should be, because in the presence of this 2-deck, we would have expected an additional magnetic signature, an enhanced magnetic moment, maybe at the interface. But mostly, as we were scanning through the different samples, we could see that there was no much difference whether we implanted the muons shallow or deep into the material. Comparing this to data which we had previously obtained on pure europium monoxide and oxygen efficient europium monoxide, we could not clearly quantify that there is any presence of a two-dimensional electron gas as it was postulated theoretically by densely functional theory. In fact, it looked that there was nothing, but that said, there are limitations to the usage of low energy muon spin rotation techniques to properties of ultra thin regions at the interfaces. So we decided that as there was no clear indication of a two-dimensional electron gas at this interface, that we would do polarized neutron reflectivity data, so do neutron scattering with polarized neutrons to have a better view on this point. But one conclusion which we drew is that one has to be very careful when trying to follow computational modeling, and as experimental results can be completely different, even if you use the best software packages. So we haven't published anything around this, so it is quite new what you hear here, but we are still working on it. And with this, I would like to stop this this talk. Is there any questions about this system?
Usually the questions are at the end.
Okay, I can do this. Right. Okay, so please then keep hold of your questions for the moment. Right. So I see that next was the superconducting diode effect. I will go to this. This is the or can I think Louis wanted the nanoparticles, and as he invited me, I have to feel obliged. Is this okay, Louis? I will share again my screen.
Yes,
so
the nanoparticles and also the superconducting will be okay. Will be
diode
nice.
effect. Okay, let's do this. I'm a bit disappointed I can't speak about the graphene or the spin polarized electron loss spectroscopy, but maybe for another time. Okay, so let's have a look on core shell magnetism in nickel oxide nanoparticles. This was already a few years ago that we have done it, but I think it is one of the neatest results which we have obtained on nanoparticles, which find a lot of applications, not necessarily now in spintronics, but really in medicine, for instance, in healthcare, such as for magnetic resonance images, targeted drug delivery, or treatment of solid tumors by hyperthermia. And for many of those applications, really, you need to determine the magnetic moment and the active magnetic volume. And so it happens that many years ago, with a colleague from biochemistry, Dr. Darton, we were trying to do targeted drug delivery. On the top left, you see results of colloidal ferromagnetic or ferrofluid in in a magnetic field as measured by an what was it, in a nuclear magnetic resonance setup. And you see the motion of the ferrofluid up an application of a magnetic field in time, and you could calculate basically the magnetic moment per nanoparticle by using what you see on the right, the Langevin formula. But often, or mainly all the time, whenever you extracted the magnetic volume and compared it to the physical volume, maybe which you get from transmission electron microscopy or X-ray diffraction, you will see that they don't fit. So the magnetic volume comes always smaller than the physical volume. So we thought, is there something to it? And devised initially, we thought we should do some experiments. And because I would always say I'm a kind of a particle physicist, which ended up to do magnetism in the condensed matter community. I thought of polarized small angle neutron scattering initially, where you would put a single layer of magnetic nanoparticles like iron oxide dispersed on a substrate, and then at shallow angles you measure the response. Unfortunately, our proposals at that time, there was only really one or were two stations in the world which had polarized small angle neutron scattering. That was, one was in Grenoble in France, and the other one was in the US. Our proposal was rejected several times, and I got increasingly furious. But in the meantime, the Americans, they came up by themselves with the idea to do this, and they used their station to do such measurements of iron oxide nanoparticles dispersed on a substrate with polarized suns. We weren't aware exactly at that time of their doing. And then one of my colleagues, a student that time, Josh and Cooper, he came with the idea and said, hey, what about, let's forget polarized small angle neutron scattering. Let's just do classical neutron diffraction.
Adrian, sorry for the
Yes.
interruption. People want to read the reference that you are provided in the bottom. Can you hide that one hide, please? Okay, thank you.
Yes, thank you. Sorry. So Newton refraction, you usually, I mean, this is like X-ray diffraction, but you need copious amount of your materials. So instead of having to produce maybe by precipitation methods a few milligrams of nanoparticles, we were faced that we would need to create grams of our nanoparticles. And we found that someone at UCL, University College London, they had developed a method to create large quantities of nanoparticles in a reactor, and they were very happy to do this by rapid thermal synthesis to provide us with nickel monoxide nanoparticle, which are antiferromagnetic. We also did this with ferromagnetic iron 304, but I think it is easier to understand the principle on nickel oxide and the analysis of the results. So that's why I will focus on nickel monoxide. So we did then TEM studies in XRD to get the average size of the nickel monoxide particles, which was about 6 nanometers, and also study their crystallinity. You see there are a single phase basically. And then we went to do a neutron diffraction, which not only provides you information about the structure as X-ray diffraction will do, but because the neutron has a spin, you can also infer information from the magnetization. And in this case, what we can see, you see the two plots at 550 nickel oxide and at 5 Kelvin, which is below the ordering, the Néel temperature of nickel oxide. You see at very small angles another peak appearing, which comes from the scattering of the neutron spin by the magnetic potential. It is therefore solely correlated to the magnetization and not to the structure. Sure, here is another slightly better view of this. To be a bit more precise, nickel monoxide is an antiferromagnet, as I said, has a sodium chloride structure for most of the times. Once you cool it below nail temperature, there is a slight tendency to move away from sodium chloride, but in large, it is still the sodium chloride structure. The nail temperature is 523 Kelvin, so the measurements at 550 were clearly taken above, and those at 5 below the ordering, antiferromagnetic ordering. The moments are in the 111 plane in nickel oxide, and we left those particles really uncoated, just to avoid incoherent scattering from hydrogen if you would somehow functionalize them. And then we used what many people would do for X-ray diffraction or neutron scattering, the Scherer equation, to get a nanoparticle size. And when you look at structural peaks, then you get basically the structural particle size of a diameter of 65 angstroms, where if you looked at the core, at the magnetic peak, this additional peak which appeared at 5 Kelvin, you got a diameter of about 51 angstroms. So there was a clear indication that indeed the magnetic volume and the structural volume are different here. We wanted then to submit this to Physical Review B, but this guy said, no, we would like you to, the referee said, we would like to have a look and understand what's going there on, whether there is some kind of spin glass behavior, that the surface behaves differently than the core. And we did had measured already some very weird magnetization loops, as it is an antiferromagnet. You see at the bottom left, at low temperatures, we observed a hysteretic behavior. And when we measured isotherms, you saw that there was something going on when it was going from a paramagnetic state, which you would maybe expect from antiferromagnet, at 375 Kelvin towards lower temperatures, towards 10 Kelvin, that you moved to a state of higher magnetic anisotropy somehow below 10 Kelvin. And it ended up, as I said, in this hysteresis loops, which are shown at the bottom at 5 Kelvin, which were measured with field cooling and zero field cooling, respectively shown in red and black, which seem to indicate some kind of competing anisotropy contributions, possibly due to spin arrangements from the core, so the nickel oxide, or from the surface. And as I said, there was one postulation that this has something to do with the spin glass or a superparamagnetic behavior. We tried to model a superparamagnetic antiferromagnet by using the Néel formula, but it didn't work very well. And then we modeled a spin glass where you make a measurement, you saturate your sample, and then you measure the decay of the remnants in time and fit this to the equation shown here. But the results gave you some unphysical results, so that it didn't seem that it had really to do anything with spin glass. That said, I must mention that there was not much more research done into spin glass in the last decades, to my knowledge. So I don't know whether more informations are in the meantime available. But finally, the referee agreed, or the referees agreed, that we had enough then convincing data and allowed to publish us. So we basically submitted this then, and I think showed that you can use this neutron diffraction, standard neutron diffraction, to extract the sizes of nanoparticles, and that we have delivered an unambiguous proof that indeed the surface layer of these nanoparticles is differently magnetized than the core. So not only have we delivered a technique which in the meantime a lot of people have started using to study the magnetic nanoparticle, but yet you can also actually quantify the thickness of this disordered shell. I mentioned that we have done also iron 304, and so you don't have to constrain yourself to antiferromagnetic nanoparticles. It can also be ferromagnetic or ferrimagnetic. We choose antiferromagnetic nickel oxide because you have no additional contribution from the magnetization to the structural peaks, which you would have in the case of a ferro or ferrimagnet. So we were able to extract pure magnetic information from our a half peak at low angles compared against pure structural information from our structural peaks. So there was no magnetic information hidden in the higher angle peaks. That's why we choose nickel oxide. We also choose nickel oxide in contrast to cobalt oxide because it is a self-terminating oxide, so there is no other oxide which forms, and we could then assume that this is all a single material. Cobalt monoxide transforms into cobalt 304, so often on the surface you would have had some other material. So that is why we choose this system, and we were very pleased finally when we were able to publish these results. So with this, I should then move, I think, to the last part, the superconducting diode effect. I think I need to share one more time. Okay. Oh no, sorry. Oh no, that was a mistake. Please bear with me. Do you see the full screen now?
Yes.
Luis? Yes?
Yes, go ahead. Yes,
yeah?
go ahead. Yes.
Okay, so I recently, so yes, I've worked for many years in the physics department, Cavendish Laboratory in the thin film magnetism group, which is now the quantum information group. But I moved recently part-time to another group, to the Center of Material Physics, which is located in Department of Material Science and Metallurgy, and work there with Professor Robinson's group. These guys have been working on superconducting thin films for a long time. So for me, it's quite a new adventure. My exposure to superconductivity has been more than 20 years ago, and through some collaboration, sometimes with Luis. But here I will talk about some results which have been recently obtained on the proximity effect and non-reciprocal transport in superconducting europium sulfide niobium thin films. So europium sulfide, similar to europium oxide, is a ferromagnetic insulator. It crystallizes in the same crystal structure. It has a lower order temperature. I think it's about 19 Kelvin, if I'm not wrong. But what the idea here is basically the penetration of triplets into an of a triplet pair into the ferromagnet. So if you look at the superconducting order parameter at the superconductor normal metal interface, which is shown on the left, for a triplet pair, there is no possibility, not in the superconductor, and hence nothing in the normal metal. So you have your singlet state, and that diffuses and dies out in the normal metal after a while. This is not the same when you replace the normal metal with the ferromagnet. Then you have some kind of oscillation. the Cooper pairs gain some center of mass momentum R, and you have some spatially modulated order parameters. So the singlet and the triplet pairs show some features in the weak polarized ferromagnet. We are really interested in the long range triplets, which go through the ferromagnet through spin rotation and spin mixing. So if you use here some kind of non-collinear spin arrangement and a non-vanishing Barry phase, you can create those in your ferromagnetic insulator, and they can carry their spin angular momentum over a very large distance. So what is this superconducting diode effect? Normally, when you have an ohmic resistance, you have a linear behavior between voltage and current, which will be your resistance, and it's depicted on the left. But if you have a superconductor, then you have a transition at a certain temperature, the critical temperature, and then you have you don't have this linear behavior anymore. You have basically an area where you have zero resistance in an ideal case of a superconductor, and then you have a critical current which sets on, and then above it you will have again an ohmic conduction. So so far so good. This is all known. The question is, can we create some kind of imbalance in the critical current, so that the current, if whether it goes in one or the other direction, is non-reciprocal? And it turns out that you can do it by creating a space inversion and time inversion. So in our particular experiment, we used niobium as a superconductor and deposited europium sulfide, as I said, as an ferromagnetic insulator, 30 nanometers, and then kept it again with niobium in a thermal evaporator, sorry, not a e-beam evaporator in a UHV chamber. These structures were grown on silicon O2 wafers. And then we measured the critical temperature of this stack to be about 5.25 Kelvin. I think this is limited by the thickness of the niobium used. We measured the coercive fields of europium sulfide to be about 45 Ersteds, and then we processed this into some kind of hole bars, which are shown at the bottom. You see there a schematic which shows you the layer, the niobium in orange, and slightly pale the europium sulfide. Then what we do is basically we pass a current through this hole bar in the direction of the red arrow, and apply perpendicular to it magnetic field H, which then, depending on the direction of the H as we sweep it, reverses the magnetization. We swept the field from about -500 to 500 Ersteds, and the current in two directions, from -5 amps to from -1.5 milliamps to 1.5 milliamps. The setup which we are using is a dry cryogenic system in which you can apply magnetic fields in this system up to 1 Tesla, and you can cool down to about 1.3 Kelvin. So it's cryogen free because you don't have to waste all the time helium. It's a recirculation setup here from a company called Cryogenics, which we have used for this. And here are the results. I don't know whether you can see it very clearly. What you see on the bottom left is the voltage current characteristics. As we alter the applied field, you see basically a kind of hysteretic behavior in your VI curves at 2 Kelvin. So below the critical temperature. At the same time, we look at basically the critical current, that is where where the halfway where the current basically shoots up, and we plot this as this is shown in the center as a dependence of the magnetic field for a positive and for the negative side of the current, and then take the difference between those two to have delta EC, the difference in the critical current, as we sweep the current and the magnetic field. So we see basically that the transport behavior, depending on the direction of the current flow and the applied magnetic field, is non-reciprocal. So we then also change a little bit the temperature and see that this is quite robust. We go here from 2 Kelvin to 2.8 and see that the behavior doesn't alter greatly. We focus next a little bit on, as I said, the difference between the positive critical current and the negative critical current and its temperature dependence. And we see, of course, that as we approach the critical temperature of 5.25, it decreases, what you would expect, because it is a superconducting effect or a proximity effect due to superconductivity and ferromagnet, which leads us to the same critical temperature at 5.25 Kelvin, which we had previously measured by the RT measurements. So what we can conclude is basically that this superconducting diode shows a large promise. So basically it has resistance, zero resistance in one direction and a finite resistance in the other, which can then be tuned basically by an applied magnetic field externally. And I think that is something which might interest the superconducting community. And I expect there will be some questions about this. Hopefully, I can answer them. But with this, basically, I would like to thank you for your attention. I would like to thank all the different students, postdocs, and professors who have worked with me on all these topics over the years, even if I wasn't able to show their work. I would like finally to also to raise attention about the book which I've published a few years ago on magnetic nanoparticles in biosensing and medicine, which contains a crash course in magnetism on the nanoscale, which I had written and published with Cambridge University Press. And with this, muchas gracias. Cualquier preguntas, do you have any questions? I'm happy to take them now. So thank you also for the invitation and your patience.
Okay, thank you very much, Dr. Adrian Ionescu, for your nice talk. Muchas gracias, Dr. Adrian Ionescu, por su excelente charla. Because we have a very big audience today, we are going to just shorten it, one question per panelist, okay? Yes, Professor Arturo Martinez says that he has not questions, but I would like to mention him just to a very short introduction to Professor Elian, who is the head of the editor-in-chief of the journal, and Professor Arturo Martinez has joined the editor board these last days. Okay, well, we are going to start then with a question with the representative from the University of San Marcos, the Dean of the Faculty of Physics of the University of San Marcos, Profesor Ángel Bustamante, decano de la Facultad de Ciencias Físicas de la Universidad Nacional Mayor de San Marcos, quien es el host de estas charlas. Ángel, your camera please, Ángel.
Hay problema con la cámara. Okay. Well, thank you very much for your conference. I think my question is about the temperatures, critical temperature in your superconductor diode. It's about 5 Kelvin or 10 Kelvin. I don't know the temperature.
5 Kelvin. I'm not very familiar with this, but there is a niobium, depending on the thickness of the film, alters its critical temperature. So if I remember correctly, so the 8 nanometer film has about 5.25 Kelvin. That is my understanding. So it's not bulk behavior. I think it's slightly higher in bulk.
Okay, thank you.
Okay. Thank you very much, Ángel Bustamante, decano de la Facultad de Ciencias Físicas de la Universidad Nacional Mayor de San Marcos. Now, very quickly, we are going to move to Professor, the representative of the University Federal of Pernambuco in Brazil, Professor Albino Aguiar. Albino?
Hello, everybody. Can you hear me? Hey, Adrian, again, nice to see you after a long time.
Thank you. I haven't seen you for a long time either.
Yeah. We are going to meet soon, I hope. Congratulations for your nice talk. I have several questions, but I will ask only one about your diode, superconducting diode. You had worked with low temperature superconductor. Yes? What about high temperatures superconductor?
We haven't investigated. We haven't investigated this yet, but I agree this would be something we would be interested to look next into. We haven't had time. This, as I mentioned, is brand new, our results. So yes, that might be something worth looking to. I don't know, yttrium barium copper oxide thin films in the proximity of that would be maybe one of the interesting features to check next, but we hadn't had time yet.
Okay, Adrian. Thank you very much. See you around.
See you soon. Muchas gracias.
Okay.
Obrigado.
Gracias.
Okay, thank you, Adrian. Do you remember Professor Albino Aguiar, who visited the University of Cambridge some years ago?
Yeah, it was him who enticed me to do some superconducting spintronics that time, but I didn't take it much into consideration until recently. So when I saw that he is the moderator today, I knew he would look forward to hear this.
Yes. Also, to mention that Professor Albino Aguiar also has recently accepted to be the member, one of the members of the boards of the journal Heat Treatment and Surface Engineering from Taylor and Francis, which is the official journal of these seminars. Okay. Well, now let's. Today we have a very special invited panelist, which is the editor-in-chief of the Heat Treatment and Surface Engineering Journal from the Taylor and Francis Online. Is Professor Delian Zhang from China. Delian?
Yeah. Hello, Luis. Yeah.
Yeah, your question?
Yeah, hello, Doctor. And then it's very nice talk. It's very interesting. Of course, my specialty is on the structure of metallic materials. So I have sort of like a superficial understanding of mechanisms. But I think probably in terms of the content of the talk, I'm most familiar with the mechanism of nanoparticles. I think it's probably coincident. So my question about the magnetic nanoparticles, if they are dispersed, or like whether the magnetic particles are affected by the medium in which the nanoparticles are dispersing, would like if they are dispersed in metals, would they have any effect on the magnetism of nanoparticles?
Not as far as I can see. If there would be in a matrix of non-magnetic metal, then I still think this core shell behavior will be there, disorganized shell and an organized antiferromagnetic core in the case of nickel oxide. I don't know whether you would house it in a ferromagnetic matrix, whether this will not have, of course, an impact, as we have seen when you apply a magnetic field, you see an organization in the magnetic spins of the shell, as indicated by the hysteresis at very low temperature, 5 Kelvin. So clearly that would have an impact. Now, if you think on organic matters, I don't think that would have, so non-magnetic materials wouldn't have. Sorry, I have here a visitor.
Hello,
Here.
hello.
Okay, okay, Delia. Okay, sorry. Disculpa me. Okay, so I don't think that the impact is so large. This core shell of the nanoparticles, this magnetic disorder on the surface seems to be there, intrinsic. It doesn't have to do anything with the environment. So in our case, we have chosen nanoparticles which were uncoated, and we have just studied them. But unless you have some kind of strong magnetic fields in the vicinity, I don't think that the results will be different.
Okay. Yeah. On the practical side, I think I've been thinking of this sort of for a few years now. Just the like if we dispersed the magnetic nanoparticles in like metals, somehow how could we make use of such kind of sort of arrangement? Because like typically metals are very non-intelligent because they are, especially the paramagnetic metals like titanium or aluminum. By dispersing these sort of magnetic nanoparticles, are we able to make this one, like how could, from your point of view, is there any sort of practical applications of such thing? Or you mentioned about the drug delivery, which is of course very nice for nanoparticles, but in terms of the magnetic signals,
our application or our interest was for application in a biological environment, for detection with biosensors, for instance, magnetic biosensors, or as I said, for the manipulation of these magnetic nanoparticles by magnetic fields in a nuclear magnetic resonance setup. And there it was important that we understand why the magnetic the magnetic size, the size structure is different to the physical structure. Application in the solid state in metals, dispersion of nanoparticles, of magnetic or ferromagnetic or antiferromagnetic nanoparticles, I haven't studied. I don't know where the applications are. I know, however, that in other fields, magnetic nanoparticles are used for ferrofluids in ferrofluidic liquids, which then are used for seals in all kind of ultra high vacuum applications. That is something to do with metals, but they are not embedded in the metals. They are just forming seals for rotational drives and linear drives. That is what we use sometimes in molecular beam epitaxy. I don't know. I'm not. I wouldn't know where other benefits would rely. Whether you could create some kind of magnetic field screening as a mu metal does, for instance. But at the moment you use there really ferromagnets with very low coercivities as mu metal shields. I don't know whether practically this could be achieved by embedding magnetic nanoparticles into a non-magnetic metal matrix. That is beyond my knowledge. I must admit I haven't looked into this, but other applications are any kind of tracing of fluid flow, which we have done in the past as well. But yes, I would need to think about this. At the moment, I don't have a clear answer to your question, sir.
Okay, thank you.
Okay, thank you very much, Professor. Thank you very much, Professor Delian Chang, who is the chief editor of the Heat Treatment and Surface Engineering of the Taylor and Francis Online. It's our pleasure to have you here today. Well, now, very quickly, we are going to move to, you know him, is from the University College of London and also from the University of Cambridge, is our friend Stuart Holmes. Stuart.
Thank you. Thank you, Adrian. Very, very interesting. Your talk's always very interesting, so thank you. I have been involved in some of the work several years ago, and I'm still interested in this possibility of producing this naturally spin polarized electron gas using your oxides. Would it be, so the question is, would it be possible to grow La lanthanum aluminate on EUO? So turn it round. Would it be possible to grow the structure that way rather than to grow EUO on a lanthanum aluminate substrate?
I think yes, there are probably people who could do this. You know whom probably I mean Thorsten Hegedal. He has grown europium monoxides by MBE. I don't think he has grown LAO on it. The true, Stuart, is which I tried to convey in the talk, is we are not sure that this 2-deck really exists. So we had, or of course we haven't presented, but we started analyzing the neutron data as well. There are some problems which we are facing there, limitations with the algorithm of the software, really. But I showed, that's why I showed just the muon data, because in the muon data already we would have been expecting that if there is a formation of a 2-deck, there should have been 2 features which we should have seen. One would have been that the information, the magnetic field inside the EO should be different to the magnetic field at the interface. So whether we implant the muons shallow or deep should have 2 different distinct signals. And secondly, you might remember that if you dope europium monoxide with electrons, you increase the Curie temperature. So we would have expected maybe the temperature behavior at the interface to be again different, but the muons didn't show us this either. So our data with the muon indicators there is no clear formation, but then there are limitations to muon implantation. You can't make the muon implantation like a delta function. You will always have a distribution. So even if you put your muons close to the interface, you will get information from the bulk or the LAO. Maybe taking the other approach to use a smaller, so to use a EUO and then grow the LAO on top of it would circumvent a little bit those problems better than the other way around. For us, it didn't work because we didn't have the facility to grow LAO really. So it was easier for us to get the LAO substrates, which you buy commercially, and we knew how to deposit EUO. So that was what we tried. But yes, maybe there are people who could do it the other way around. Now, that said, as I mentioned, we did neutron data, which I haven't presented, and that is also inconclusive, but I can't tell you more because the problem is we realized when you go to such areas, has become apparent. There was, I would have discussed this in the graphene section. When you come that the effects which you are looking for, if your film, like a graphene layer, or your interface is thinner than the roughness, or on similar large or a similar scale, you start to run into problem in the analyzing the data, and you have to alter the algorithm which people usually use when they do Newton optics. And that wasn't the case until a few years back when the first people like us started running into those problems. So the last few years, we tried to advance the technology to understand when you take neutron data from such thin films where the thickness, like in this case, the interface, the postulated 2-deck, they said is 1 or 2 nanometers they expected in the theory papers. And this is almost on the size of the roughness between the 2 films. So when you run into these problems, you can get unphysical results from your software when you fit the data. And that was what happened. Our magnetic scattering length density showed negative values, which is impossible in physics terms. So we realized that, but this is not us. I mean, there are guys who write the software, that this software has to be rewritten to address this problem. And that's what happened. So we're looking forward, maybe, shortly to revisit this with Razan. There is a software now which is called Ref1D, and then we will have a better clue what's going on. At the moment, I'm quite downbeat that actually there is a intrinsic 2-deck spin polarized created there at this interface naturally. But I mean, nowadays we have the technology, molecular beam epitaxy, chemical vapor deposition, that you can control, and you can deposit two-dimensional ferromagnets in a much better controlled way than to rely that such a thing appears at the interface naturally. It would have been nice. That would have been clearly, because you would have had all the ingredients together and off you go. We are not sure that this is really working, unfortunately.
Okay. Thank you, Adrian. Thank you.
Okay, thank you very much, Stuart Holmes from the University of College of London and University of Cambridge. Okay, Adrian, we have today some students from the Eurasian National University, which is in Kazakhstan. From Kazakhstan. They are also asked questions.
Dobre dia, or is it merhaba? I don't know.
Simbad Utelbayera. Simbad, open your camera, please, and your question. Simbad. Are you there? It's not there. Well, let's continue with the other one. Damir Tukaibai. Damir.
Can you hear me?
Yes.
Yeah, go ahead.
Yes. Hello. I liked your presentation. Your first topic was interesting to me. Spintronics. I'm thinking to take this topic as my research, specifically Heisler alloys, Heisler compounds. So I want to ask you, as experienced, your opinion, advice about this Heisler alloys. Should I take it? Should I focus on it when I take my subject, my research as spintronics, or should I focus on something else when I take spintronics?
Can I double check? You mean Heisler alloys?
Yes, Heisler compounds. Yes.
Well, this was part of my PhD. my doctorate thesis was on Heisler alloys. Stuart Holmes, who just asked, he also worked with Heisler. They held at that time large promise as being 100% spin polarized materials, and hence were researched. They have other fantastic applications as in shape memory alloys. I know that they are doing this, but somehow in spintronics they never made the breakthrough. So while they showed high spin polarization, the expected 100% spin polarization was never ever mentioned, and there were different arguments pro and co, maybe with the termination and so on. And then I think many people moved to other materials which delivered them 100% spin polarization, or other problems emerged which were more interesting than now optimizing Heisler alloys. By themselves, they are a fantastic class of materials. One of my collaborators, which was on the nickel oxide talk, Professor Kurt Ziebeck, he was one of the godfathers of Heisler alloys in bulk form, and he has done a lot of research on them. And I know that people use them they want to use them in medical application as shape memory alloys. So basically altering their shape by applying a magnetic field for inserts in your body. So I think there is a lot of application possibility. There might still be a need, for if indeed they show high spin polarization, because they have usually high ordering temperature, high Curie points. That what made them so interesting. Europium oxide being 100% spin polarized has 70 Kelvin, whereas most of those guys are in excess of room temperature as a Curie temperature. So it depends what you want to do with them. I think it still warrants looking at them. I think cobalt manganese silicon was one of the highest Curie temperature Heuslers, which some people looked as a spin injection electrodes into it. So it depends on you whether you have an interest in this or not. Surely, there is scope. There is scope for these materials.
So thank you. So from my understanding, it is kind of outdated material right now, but it is easy for beginners if I take spintronics as my research.
It's not easy. I don't say that it's outdated. I mean, things come forth and back. It's like in fashion. It was once interesting, then it gets forgotten, and then it comes back. So I never say outdated, but people have started focusing on other aspects rather than improving the spin polarization of Heusler alloys as spin injection electrodes. It doesn't mean that in 10 years' time, maybe they start looking at this as well, because they have some advantages against just pure iron. But often people don't then go through the full pain of, I mean, a Heusler is a tertiary alloy. And if, I don't know whether you want to do it in bulk or in thin films, controlling the stoichiometry in thin films of such alloys is more tricky than just evaporating iron. So people then just say, okay, what's the point? I'm going to use iron, has 43 or whatever, 42% spin polarization, and I can still get something done with it. There will be always scope in material science, to try to improve and maybe understand why maybe the 100% spin polarization has never been obtained. The 100% spin polarization was always theoretically predicted from band structure calculations. And as I said with the europium oxide LAO talk, one has to be careful when you have obtained results by modeling, whether they represent the reality. You never know for sure, right? So maybe they are not fully 100% spin polarized. They have spin polarization higher than iron, but whether it's 100%, that has to be seen. It depends really. I mean, if you want to do a PhD or or a master, it doesn't really matter what you are doing as long as you like what you are doing. So if you can get the motivation for 1 or 2, 3 years, depending on if it's a master or PhD, to do it, it doesn't matter which material system you are doing to start with, and get into the area. As I said, I started with Heuslers alloys and then moved into other materials.
Okay.
Yes, thank you.
Thank you, Damir. Ismailov Yerbolat. Ismailov Yerbolat. Your camera, please. It's not there. Okay. Mekevai Kwan Gisbek. Mekevai. Your camera, please.
Hello, everyone.
Hello.
Thank you very much for your presentation. It was very interesting. I not have question.
You don't have, okay.
Okay, don't worry.
These are my preferred questions.
Okay. Korkitov Nurajlet. Korkitov.
Hello, teacher.
Your camera, please. Your camera.
Just a moment. Hello, teacher. His topic is very interesting. My question is, why is the increase in the moment M and P in GFC cycles?
Why is there an increase in the moment? Sorry, can you? I couldn't hear the rest. Could you please repeat? Why is there an increase in the moment?
Just a moment.
Just repeat the question, please. Korkitov, can you repeat the question, please? Maybe has some problems with the signal. Okay, has problem with the signal. Okay. Diana Nebek-Shanova. Diana. Diana. Not there? Okay, any other member from the Eurasian National University, Kazakhstan? Yeah, apparently the internet has broken there. Okay, now today we have some invite from the student there. Now the question from the public online. The question from the public online. From the University of San Marcos, the public, James Godoy. James.
Ok, perdón. No tenemos preguntas de las redes sociales, solo felicitaciones por la presentación del profesor Adrián. Saludos.
Muchas gracias, señor. Sí.
Okay, from Colombia, the Republic of Colombia, from the Eliana.
Muchas gracias, señoras. Todos buenos a vosotros.
Ok. Ximena, la otra red.
Muy buenos días. No, por este lado tampoco tenemos preguntas. Hay muchísimos agradecimientos. Pues aquí tenemos una línea muy grande de eso y pues varios estudiantes están entusiasmados con el tema. Muchísimas gracias, profesor, por haber tocado ese tópico.
Okay. I think that there is one here. Simbad, are you there? I think not here. Anyway, from Arturo Martinez already left, I think, from Mexico. Okay, it's not here. Arturo already left, I think, because he has some things to do. Okay, Adrian, thank you very much for all your patience and your solving the questions. On behalf of the Red Latinoamericana de Física de Materia Condensada y Ciencia de los Materiales. Entonces, we would like to thank to you, and we appreciate you took your time for us for today and to give us these small topics and very illustrative for now. Okay, now everybody please open your camera. Todos abran sus cámaras, por favor. Open your cameras to say goodbye to Dr. Adrian Ionescu. Open your cameras, please, everybody.
Yeah,
everybody,
hello. Goodbye. Goodbye, Dr.
Thank you, everybody.
Goodbye.
Thank you very much. Muchas gracias, señores.
Arrivederci, tutti.
Nice. Hello, Professor.
Thank you very much for the invitation, guys. It was a great pleasure. And I'm looking forward to sit in the panel and listen to the talks in the future.
You know that there is a possibility that we organize the second Latin American conference on superconductivity and magnetism in Ayacucho, in Peru. there is a possibility that because we spoke with the University of Wanta authorities, and they are happy to support or be one of the sponsors. We are going to speak in more detail during the next months in order to organize that next year. In this moment, I am in the Kazakhstan, visiting the Eurasian National University in Kazakhstan, and working very hard these days, and we're coming back in the end of this month to Cambridge. Okay, my friends. See you very much. Goodbye.
I'll see you.
Ciao, ciao.
Bye.
Bye. Hopefully, Ayacucho then. Bye-bye.
Bye-bye.
Goodbye. Thanks.
Melvin, cierra la transmisión, por favor.